So as I was saying, this is it's making up the exam, and I kind of just got it ready better for next time this is taught. So your guys' equation sheet is almost identical to this, except it's missing this table. So if you need the table, I'll give it to you. And then it's missing these equations on rotational motion. And pretty much, you need to know those bottom two equations, right? So if you take this class again the next time it's taught, you won't have to know them, but you guys do. It's not on your equation sheet, so I'm going to stick with that. But remember the magnet. Why were these equations important? The magnitude of angular momentum, the square root of L times L plus 1 times h bar, and the z component of angular momentum is m sub L h bar. Why were those big deals?
For projections.
For projections. Remember to draw those? So you find out what, this is all about rotational motion. So you find out what the little quantum number, m sub L, and m sub L depends on the quantum number L. And they give you an L, you figure out what the m sub L's are, and you can write all the projections. Remember doing that? Okay, so that could very well be on there. Okay. What quantum number describes all this stuff? Like, if you jump up to particle in a box, what's the quantum number? Not for particle in a box. Yeah, just pretty much all you do is you dig on the equation sheet and find the equation for the energy. And you look for the quantum number. So it's little n. How about harmonic oscillator? Little v, right? How about rotational motion? Here you might have to dig in your notes. Or if you have really good eyes. It's that cursive L. Because for rotational motion, E equals L times L plus 1 times h bar squared over 2I. And that's in your notes somewhere. Okay, we talked about that a little bit. So those are the quantum numbers. And then if you wanted, jump back up to particle in a box, if you wanted to write a wave function for particle in a box, I would have to tell you what? I'd have to tell you what little n is. And then you look at the equation sheet to write the wave function, right? Everybody with me so far? Gloriana, you see what I'm talking about?
Yes.
Okay. I tell you it's a harmonic oscillator. I'm going to have to tell you what?
The 0 point energy?
If you have to write a wave function, I have to tell you what? If you're going to write a wave function for the harmonic oscillator, I have to tell you what? Okay. Do you just look at the wave function? And it has that h in it?
The Hamiltonian polynomial?
What was the h called in this wave function for a harmonic oscillator? A blank polynomial. They live in holes. We add an e on the end.
No.
Not Hermit, but Hermite. Hermite polynomials, right? That HV, and you get it from this table. What was the n? Again, it's in your notes, so I would have to normalization constant. And they don't have a table of those. You have to actually find them, I guess. Okay. So, and then rotational motion. Well, we didn't really mess with that too much, but for its wave functions. But all the questions that can be asked, I mean, it could say to normalize. All those starting points I would know, right? Like, what's the starting point if the question is normalize this? Where do you start? Equals 1. And you're in your wave function there, you have this normalization constant that ends up being squared out front, right? That's the following step. What if it said, find the energy? Here's the wave function. How do you find the energy levels? What would you do? Okay, but in the general, what general expression would you write to start out? That bra and the ket, that expectation value equation, exactly. So you have the, right, and then it equals the integral of psi star operator psi d tau. Okay, what if I said, what's the starting point if I said, show that these two wave functions are orthogonal? Jeffrey, what would be the starting point? You haven't said anything yet.
The integral of, or from negative infinity to infinity, of psi star a times psi b.
Yeah, whatever they are, d tau. And that integral has to equal what?
0.
0. Right, the integral, they have to do two wave functions. The first one's complex conjugate. Integral of psi star a times psi b d tau, whatever you like to write, has to equal 0. What else have we done? What were the common operators that you could see in a homework question that I could ask and say, hey, the expectation value or the average? Okay, there's p hat. There's h hat, yep. P hat squared. I could make one up, like m hat, and you'd add 6 or something, right? So just know those general starting points, and you should be able to start every single one of those. Then it'll just turn into a math problem after that. Those were just some big picture thoughts. That equation's messed up. The h bar should be outside the square root. All right?
Yeah.
Ah. Let's see if I can fix that. There it is. Okay. So did you have any questions on the homework? And any problems that you'd like to work over? Oh, we had 0 point, well, that's concepts. I can go that route too if you'd like. What, since the exam is mostly problem-based, I can give you some sample problems. We can talk about problems that you had assigned. We can do conceptual stuff.
There's no concepts on this?
Yeah, I can ask concepts. There's a lot of concepts I could ask. Could make us some problems like this one. Yeah, right, lab time. So lab time is 9. So that way you have all day. Well, you have plenty of time. So did you have no homework questions? You got them all figured out? I can make one up.
Are we gonna have to draw anything?
Oh, yeah, like the projection one.
If it's in the homework, if you're asked to do it in the homework or the concept preview, it's totally free game.
Can we try doing that one?
Can we try that?
Okay, let's not draw to scale. Like 12.16. Okay. Let's draw them for, well, I did the, oh, I can be really specific. ABC part D. So draw a scale vector diagram to represent the state. Let's say L equals 3, M sub L equals -2. So not scale, just draw a vector diagram. L is 3, M sub L is -2. Very often, I think the homework also asked you draw draw all the states for, and they didn't give you the M sub L, they just gave you the L. So then you, like if, for example, if I didn't give you this part, how many drawings would you have to do? Yeah, including M sub L is 0, that'd be 7, right? From -3 all the way up to +3. That'd be 7 drawings you'd have to make. So instead of having you draw 7 of them, let's just have you draw one of those 7. Okay, so what would you draw?
Which one do you want us to draw?
L, draw the vector diagram to represent the state L equals 3, M sub L equals -2. Right? I have to give you, if I don't give you an M sub L, that means draw them all.
How do you want to draw -2?
So in this case, you're just going to draw how many pictures? Just one picture, one projection.
Why only one?
Because each projection needs an L value and an M sub L value. So if you draw projections for L equals 3, then remember the magnitude of the angular momentum was L times L plus 1 square root times h bar. That was the length of your arrow, right? So you kind of drew it like this, z-axis. But M sub L is a -2, so I wouldn't draw it up. I'd draw it going down. So this, this describes the length of your arrow.
So Dr. Smith, we don't, because on the homework, like on the record work, we don't include the h bar, do we?
Yeah, you should. What 3 plus 1 is 4 times 3 is 12. So this
The square root of that is only 3.46.
square root of 12 h bar is what that guy should be. If you want to put a decimal there, that's fine.
Oh, okay.
Right? But it should be the square root of 12 h bar, whatever the square root of 12 is. And then over here, you should label it, this length you should label what? -2 h bar. That's why we drew it down, because M sub L is -2. So the angular momenta is in that orientation in space. It's just stuck there.
Would you be okay with us leaving the angular momentum as square root of 12 h bar to actually solve it out?
Oh, it's fine.
That's fine.
Does this, hey, here's a question for you. Okay, you have all these little molecules, right, rotating or whatever the object is, right, doing this three-dimensional motion. And let's say somehow, and it's not possible, but somehow, because remember they're degenerate, all these states are degenerate because the energy only depends on what quantum number?
Okay. Oh.
For a particle in a box, yes, L, right? So all of these are degenerate. If you drew all 7 projections, they're all the same energy, okay? But, okay, that's fine if you want to picture them all. That's a lot of different orientations to the picture. So I guess if somehow if they could just be fixed onto one state somehow, does that mean, and you had a bottle of this stuff, does that mean they're all, their angular momenta is all pointing down in that direction? They're all identical?
It's only pointing down because L is negative.
Because this is an orientation in space. It's fixed. And remember, it's angular momenta too. So then it's this abstract concept of a bicycle wheel spinning such that the right-hand rule makes it go like that, right? So it's kind of spinning out. You have this rotational motion. It's going like this, so that the right-hand rule makes it go like that, right? So does that mean that every single molecule is oriented in this way?
Just pertaining to that M sub L?
Would it? I could, I could have that bottle and every single molecule in it, every single rotating body in it, is oriented in the same direction if I applied what to this bottle? Because right now, if without this magical thing that's applied to this bottle, they all have this angle at some arbitrary axis. They're all over the place, but they all have the same angular momentum at this arbitrary axis. Whenever you identify any one of them, they're going to have this same angle at that arbitrary axis. But if I apply a rotating charge, acts like a little tiny NMR people,
Magnetic field.
acts like a little magnet. These little spinning charges act like a magnet. So the only way, if I want to get them, I can, and it's true, they would all be perfectly lined up. They would all be in the same orientation in that bottle if I applied a strong enough magnetic field. That's your NMR spectroscopy there. Turning that field on and off and monitoring the decay, monitoring the precession. But that's, I don't think you need to worry about that, but that's the idea there. So you're not going to see it without the magnetic field. That's it. You have to apply it, an external magnetic field.
So Dr. Smith, for those projections, if you just give us L, and you say like draw a state, and you just like L equals
Yeah,
4.
pretty much you're just going to draw stuff that looks like this. If I said L is 4, you're going to have a lot of drawings if I don't tell you the M sub L also.
So then what would we use for the next one?
You don't have any choice. You have to go from, M sub L is going to go from negative L to positive L. And don't forget to include 0. So if L is 4, you'd have 9 drawings to do. See how easy these, let me give you an example. You may not want to do this, but it's not a bad idea. Let me show you how easy these exams are to write. A trial wave function of a particle of one-dimensional box is in the form, XL, right? Okay, and now, man, I just gave you a whole exam right here, well, a lot of exam questions, right? I want you to calculate, I want you to normalize it. I want you to find the average momentum. I want you to calculate the average energy, right? And all that's just by changing one little part. And notice how these trial functions, they, they're not all the same. I mean, there are some functions that are better than others. In the real world, they'll model a lot better. Okay, so I don't think this one will that well, but okay. How did you want to spend your time here? Can I ask you some questions? You can work this out.
Any concepts?
How would you do this? That's where you'd start. Then you'd write yeah, there it is. Right?
So it would just be XL squared?
Mm-hmm. Well, don't forget about n squared and the L squared pull out of there. Right?
You can put out L squared?
I think this is a good one. I think if you don't want to do concepts, I think this is a great way to spend the time you got. Right? And then average momentum. So what would you like to do? Mel, what would you like to do? Gloriana, what would you like to do? Are the energy levels of a particle in a box evenly spaced?
No.
Here's a good question. The energy levels, I'm not going to respond to it yet. The energy, I don't know, I want to reword my question. The energy levels of what system are evenly spaced?
Oscillator.
Yeah, the what oscillator? Harmonic oscillator. How about, right? This tells you right here. There's no quantum number in there. It's always h bar omega. How about this? It's given to you on the exam. And you see the different energy levels there, right? On each energy level, I want you to sketch the wave function with a pencil. And then on each energy level, I want you to sketch with a pen, I don't know, a black pen or something, the probability density. How would you do that? See if you can figure it out. On each energy level, I want you to sketch the wave function. Part B, on each energy level, I want you to sketch the probability density. And to do that, you pretty much have to understand what this diagram is all about in the first place, what the white regions meant and what the darker regions meant.
White regions are the nodes.
White regions were the nodes. That's where the wave function has to equal 0. Exactly.
And the darker regions will be where the tallest peak of
Yes. Whether it's top or whether it's positive or negative, it's a peak. In the wave function, yes.
That's the wave function, so what about probability density?
So probability density, to me, that's the easy one. The wave function can be the complicated one, because with the probability density, all you do is just make everything positive, right? Because the negative times the negative is a positive, so all you have is positive peaks. The zeros are still 0, because when psi is 0, psi times 0 times 0 is 0. So, for example, for the bottom one, the wave function has to have only one hump. Either you can draw the hump going down, or you can draw the hump going up. Right? Either one works. And then the probability density has to be one hump going up. Okay, and if you wanted to be more technical about it, you should probably try to make it a little more narrow and sharp, but it works. And then for v equals 1, how would you draw it? 2 humps.
One going down.
By one going down. So however you want to do it. Just make sure that it crosses 0 in the center. So the whole thing, this is assuming that's your x-axis, right? It's assuming that this is your x-axis. So it's crossing 0 at the center. And then the probability density right? And do that for each level. if you can put anything on the test, that if I wanted you to find find the normalized v equals 1, what would you do? Now this is easier than the test because it's sitting there right next to the equation, but what would you do? What would you do? So I want you to find the normalized wave function for v equals 1 for a harmonic oscillator. And I may not, the English may not even say all that. It's just the big giveaway is the v. That's your quantum number. Yeah, that HV of, so what are you going to put in for HV of y? 2y. And then it's times, yeah, e to the minus y squared over 2, right? Is there any, when you do psi star psi, is there any, does the star do anything? No, there's no i's. And then you have a y times, don't let that scare you. We've done those integrals. Whoop. Where was that stuff? Here. They're nice. These integrals are awesome because notice how you don't, your limits are taken care for you. You do just do n factorial over a to the n plus 1. So those are nice integrals. And then you'd figure out what your, here it is, and then you'd figure out what your, so that's the weird thing about this. I've always thought it as weird, is that's your normalization constant. Usually they give you a number, right? They give you a table, they give you something, but here they're making you find it every single time. So if you wanted to use the v equals 2 state, you have to first normalize it and find what n with a little 2 on it is. And then you can go ahead and use it. And then if you did find it, I could say, hey, show me that these two are orthogonal. What would you do? You went through all this work to find these normalized wave functions, only to show that they're orthogonal.
So the integral of the psi would be 1 times psi v2.
Yeah, and you should get 0. But it wouldn't be that bad because these exponentials are additive. Right? I don't think it'd be that bad. But that's bad as subjective, right? Whatever we ever think is evil. What if I said, okay, you went through all this work to find this guy. He shouldn't be that bad. You went through all that work to find him. Okay? So that means you had to normalize it, get what the n1 is. You with me so far? Okay, now I said, find the expectation value of p hat squared. How would you set it up? How would you set it up?
Or just do what the regular p hat equation is and square everything in it. So the h bar squared over
Yeah.
equals, and it'll be
dd. I guess it's ddy, right? Well, because there's everything's in terms of y, so I'll put a y in there, and then you got to square that. So that is p hat. Well, that would be p hat squared. So this really is, p hat squared is really best written how? I guess it's this thing squared, but you can't apply this. I mean, how do you stick that in an integral? It's a lot easier to, this is equal to what? You're going to, multiply this by itself, what would you get?
Negative h bar.
Negative h bar squared times,
D squared over.
yeah,
dy.
the second derivative, d2 dy squared. Exactly. That's what p hat squared really is. So you'd have to set it up, expectation value of p hat. And then inside here, inside there, you'd put negative h bar squared, second derivative. Right. Psi 1. Right?
What function would you use to find n for that? Yeah.
To-
The one on the very end?
To find, so in each case with that harmonic oscillator, this is where I think it's funky, because look at for particle in a box. If I said pick an n and write the wave function, man, it's no big deal. There's nothing for you to do, right? It has the same normalization constant every single time. You just plug it in. You know, right? For write psi 3, well, you just put in a 3 for n and you're done. But harmonic oscillator, ouch. Where'd it go? So if you wanted to, you're talking about this one, for example? Well, really any of them, they're all the same. So you have to find that normalization constant. So you have to set this up, that 1 equals the integral psi star psi d tau. And here's your psi, this whole thing. And they already put in the normalization constant for you. That's the n. So you pull out that n squared, and you just have to solve for it. I think that was one of the homework questions. I don't remember. But even if it wasn't, you'd know what to do. That'd be a good handout to do, if you can do that. It never had you do it, did it? But that's why I think it's so important to know those initial points. Know those initial starting points. Normalization, right? Average, which is the same as expectation value, right? So that was the operator story. What was that? Orthogonal. Right? So those are pretty much it. If you write those initial points, the rest aren't so bad. You just use the equation sheet to write the wave function. What was wrong with this picture? Yeah, right, the right-hand rule. What was this picture trying to show? What's this picture trying to show?
Possible wave function?
Yeah, how?
Not the top one.
Yeah, not the top one, because it's supposed to be motion on a ring or something, right?
Mm-hmm.
So it needs to
End up where it started.
should end up where it started, exactly. If it doesn't, then it's not going to work. Are these valid wave functions for a particle on a ring? Mm-hmm. Yeah. What I think is kind of weird is this part right here. What the heck is that doing there? Right? Thank you. Right? Does that make sense? What is this stuff doing there? Maybe it's to make it more, give it some thickness. Maybe that's what it's for. I don't know. I don't really see it, but because it's 2 dimensions, so it's not 3. So I don't know why they make it, give it that thickness. And then we did 3 dimensions. Thank goodness we didn't have to do all this stuff, right? They just gave us the answers. Okay. Yeah, projections. Talk about fermions and bosons. I don't think it'll be too bad. It's just, I don't want you to get thrown and not know where to start on something, right? Because there's so many problems. I mean, look how general these are. But there's the same thing again and again and again. If you just know those starting points, the rest is just math. It's very doable. So the tools of this quantum mechanics aren't so bad. It's just that the math can get you. Well, this is probably going to put Alyssa to sleep, this help session. But she probably needs to sleep. So. Kevin's falling asleep. What do you want to do? Is that about it? Had enough?
Is that it for concepts?
Oh, I can ask you some more concepts. If you want to change the period of a pendulum, how would you do it? Or can you change the period of a pendulum?
Increase frequency.
Change the length of the
Changing the period of a pendulum would be changing the frequency. So that's kind of like just saying the same question again. How can I change the frequency? How can I change the period? It's the same question.
change the length of the string.
You could change the length of the pendulum. That would work.
Bigger string.
Bigger.
Okay. Any concept?
Change gravity.
Yeah, I see what you're saying though, Kevin, but see how the problem is that we said pendulum. So we're not talking about the harmonic motion of this. We're talking about the harmonic motion of this. So you only have 2 choices, and Jeff's right. Either you change L or you change G. Well, you can go.
Not here.
Yes, you can. How can you change gravity?
Vacuum.
Go
Higher.
higher. G's different, right?
So you now want very small.
Technically, yeah, all right, fine. What is the technical jargon for why energy is quantized? Without this, energy cannot be quantized, mathematically speaking. Without this, you can have an electron, fine. You can make it as small as you want, fine. But without this, you're not going to have quantized energy levels. Energy won't be quantized. You need to have what?
Uniform energy.
That's just a consequence of the energy.
Which is a quantum number?
You get that again as a consequence of having the quantized energy. It's quantum numbers. What is the mathematical condition?
Oh, boundaries.
Boundaries. You got to have boundaries. If you don't have boundaries, you're not going to... It's like an electron flying in the air for free. There's no boundaries. It's not in a bond. It's free. So you need to have boundary conditions in order to quantize energy. There has to be boundary conditions. If why can't we have this pencil, or put a marble in between two objects here, right? Have it roll around, give it some motion, have it roll around in there. Why don't we see it? Why don't we see its quantized energy levels? Why don't we see it? Oh, the ball spending most of the time in the center, or disappearing here and appearing there, right? And all these possible locations, giving it more energy. Why don't we see quantized energy with a marble in a box? And all you have to look at is this.
Because the separation of energy levels is really small compared to the marble.
Separation of energy levels is really, really, really small. Yeah, but why? Yes, I think I would accept that answer. But why? Why mathematically? Looking at their end result here. Whether you look here or whether you look here, it's the same answer.
It's mass.
It's mass, because in order for this to work, we're talking about mass of what?
An electron.
An electron, which is 10 to the negative 19 or something? Yeah.
31.
Negative 31? I don't remember. It's really, really small, right? Marble, it's not, right? It's not a kilogram, but it's not, it's probably 0.01 grams or something, right? It's too big. The M is huge. What else is huge for that marble? Yeah, that L. The L is huge. So those energy separations, exactly, they're just really, really small. What was going on here? Is this a wave function or is that a probability density? That plot that I circled. It's a wave function. So how, I said, okay, now here's your wave function, draw the probability density. What would you do? Yeah, but they're going to be really tiny though, right? So well, they actually be 3, right? They're really tiny though. Area corresponds to the probability density, where it might be. So that means that, can it be outside that box? Yeah. Very low probability, but it's possible. Really important, because if you don't take this into account, then all your results are off. Quantum mechanics has to have all these possibilities, right? And it could be outside the box. So physically, what that means is, I'll take my little doohickey here. Now, that's not the good idea. You should probably have like a hunk of iron or something, because that'll last a lot longer than a little rubber thumb thing. So you have a hunk of iron sitting there. Well, oh, a stapler. Okay, stapler, that's more iron. So in order for it to go, and we could have an infinite amount of energy, whatever, but the idea is it's here. It's not over here. But the probability of it being over here, I mean, what is it, infinitesimal? Essentially, you can't even measure, it's zero. But the point is if you wait long enough, and I think we said something like this, is like the cat exists. Remember I talked about this? Maybe I didn't.
Existing on the sun.
The cat existing on the surface of the sun for, and I forget the article because we haven't read these articles yet, or we skipped them or something. It was like for 90 seconds, 90.2 is some exact term. For some impossible amount of time, that's the same as this stapler existing over here. So if it was over here, well, then it goes back. The point is that it just kind of gets knocked over because it was supposed to be over here, now it's over there. So if you wait that long, or that probability of a cat existing on the surface of the sun for 90 seconds, it's crazy. So and they believe that's what's going on. This tunneling, it's important to take those things into account. We see it. Electrons do energetically impossible things with scanning, tunneling, microscopy. That's tunneling. It's in the name. What were the two forms of energy that you can kind of use to describe the harmonic motion? Potential and kinetic. Yeah. If you're going to draw the energy levels, what would you end up drawing? How would you draw the energy? I give you the parabolic potential. I say sketch the energy levels for a harmonic oscillator. What would you draw? Go ahead and sketch the energy levels for a harmonic oscillator. Anything evenly spaced is acceptable. You can draw, just have to be evenly spaced, and I can't take anything off. That's probably enough, right? Almost there anyway. Oh, here, the guy with the big stick. Why does he have the big stick? Oh my gosh. Angular momentum allows him to do it. How? What was the equation for angular momenta? The length of it has a lot to do with it. Yeah. So the longer that radius is, the more angular momentum you have. So he has to apply a lot of torque to actually twist that big long pole. So he's just walking along. I mean, it's almost like holding two iron rods here, two ropes as he's going across, because he has to really apply a lot of torque to get that thing to move. So, I mean, just imagine if you had two ropes going alongside him and he just has his hands going along. That's pretty much all he's doing, because he can push down on that stuff. It's not going to, he's fine. Now take that big long stick away from him and have him walk across. Now that's what would be amazing. Okay. I would think the wind would really hurt with that big long stick, but I don't know. That's the trick. I still wouldn't do it. All right, so have a good day.